Typically, when you have a reaction, the profiles for the reactants and products would look like this. Which curve? This is concentration of reactant or product versus time. Which curve here would represent the reactant and which one would represent a product? The red curve would represent reactant and the blue curve would represent your product. Okay? So when is this reaction fastest? At the beginning, right? Where the slope of your curve is steepest. And when is its lowest? Over time, concentrations level up, the rate of the reactions, uh, the rate of the reaction essentially goes to zero. We say when that happens, we say we've reached equilibrium. Okay, so equilibrium at the molecular level, what actually happens is the reaction has not really stopped. Forward reaction is still going, except that reactions are reversible. So what we're saying is at equilibrium, the forward reaction is occurring as fast as the reverse reaction. So overall, you don't see any net change in your reaction mixture. Okay? So no further changes are observed. So chemical equilibrium, we say, is a dynamic equilibrium. Okay? At the microscopic level, at the atomic level, nothing has really stopped. The reactions are still going on, except that the forward and reverse reactions are going at the same rate. Why is the reactant not completely used up in this particular example? You'll notice your reactant levels off at some value, not zero. Okay? Typically, that would be the case because sometimes depends on how, because that would depend on how fast the forward and reverse reactions occur. Okay, so we say reaction is essentially complete if the reverse reaction is very slow compared, is the rate constant. Remember we talked about kinetics. The rate constant of the reverse reaction is very small compared to the rate constant of the uh, forward reaction. If you remember, we said the rate for the forward reaction, let's say if you have something as simple as R going to P, let's say you have an elementary step, right? So the rate of the forward reaction would be what? B forward would be K times concentration of R, right? K forward. We're going to label that with an F. And the rate of the reverse reaction would be equal to K of the reverse reaction times the concentration of the product. We say at equilibrium, these two are equal, okay? This and this are equal at equilibrium. And then what would you say would happen? If those two are equal, then you say Kf times R must be equal to Kr times P at equilibrium. Okay? So you say Kf over Kr is equal to P, concentration of P over concentration of R. Okay? So what what would be the conditions that would lead to a preponderance or predominance of product at equilibrium? If we want a lot of products at equilibrium, how would the Kf and the Kr be related? If you want this ratio right here to be really big, that means Kf, if Kf is much, much larger than Kr, then you say your reaction is essentially complete, right? This ratio is going to be a very big number if Kf is much, much larger than Kr. So the extent to which your reaction goes all the way to the product side depends on your rate constants. But the rates at equilibrium for forward and reverse are equal. Okay? It's the rate constants that determine how fast the reaction, how far the reaction will go. So here's a quick question, clicker question that will check your understanding of the concept of equilibrium. Consider a reaction illustrated here. This is at time 0, 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes. What's happening here? Your red atoms are being converted to what? It's changing to blue, right? So what's happening here? From time 0 to time 2 minutes, what happened? You lost how many red atoms? You've lost 4 red atoms, okay? And they're now converted into molecules. I colored the molecules blue just to emphasize that they've been turned into molecules, okay? So that's your reaction right there. So if you have the reaction here is you have two red atoms exchanging to a blue molecule, right? Or an R2 molecule, you can say. That's your reaction. So when did this reaction reach equilibrium? Between 2 and 4 minutes, at 4 minutes, between 4 and 6 minutes, or after 6 minutes? All right, let's see. 50-50. What's the popular answers? A and B? All right. Okay. Um, let's convince your neighbor your answer is right. Who picked A and who picked B? Okay. Why did you pick B? Okay, so there hasn't been any change since 4 minutes. Okay, what about you, Brandon? Okay. All right, so let's do the redo the poll. A is the better answer, right? You know, at 4, it's at equilibrium, right? It hasn't changed since 4 until 10 minutes, but you don't know if that could have happened before the 4-minute mark. You know it's happened somewhere between the 2-minute mark and the 4-minute mark, okay?